Is that okay now?
Yes, it's okay.
Great. Okay, well, thank you very much, Rasha, for the introduction. And it's nice to be here again. It's my second time, of course, virtually to meet you. And I hope that in the future we should be in a position to meet in person. So what I would like to do is, as Rasha mentioned, I'm going to talk about bio or nature-inspired swarm intelligence with applications. So this particular presentation will comprise the following elements. I'll give a brief introduction to the subject matter, and then we'll bring in fact, 3 algorithms in the context of swarm intelligence. I'll introduce those individually and we'll apply them to certain applications, which hopefully will be interesting to you, and then we'll conclude the presentation. So swarm intelligence actually comprises the following things. So there are living species which collaborate with one another, and they work collectively with one another to help, in fact, one another towards a certain goal. And of course, with these living species, the usual goal is to search for sources of food. So we talk about bees, for example. On the one hand, they have a mechanism of communicating with one another. For example, when a bee discovers a source of food, it returns back to the hive and performs a certain dance, and that's an indication to let the others know that this individual has discovered sources of food. Bees, in the same way, when they travel along a particular path, they leave some kind of chemical called pheromone, which again is an indication for other fellow ants, in fact, to tell them, you know, that this ant has been on this particular path. And so, of course, the strength of the chemical will let the other ants how far in time the individual ant has been on the road, of course, and so you see a trail of these ants, you know, following a certain path. Fireflies, of course, have got this luminance sort of mechanism, and so on. But after all, of course, what it is these are actually species help and collaborate with one another through these communication mechanisms to find a certain source of food. From an engineering perspective, what we would like to do and what we do is we translate these phenomena, these phenomena in these living species into mathematical formulae and into optimization algorithms. And the idea is basically in a control context, for example, we normally will be looking at a minimum of an error, for example. So you would normally have a particular controller to design, and when you run the controller, of course, the system would have to reach a certain minimum point. For example, these are some of the search spaces, which are very complex, of course. A lot of local minima are there, where the traditional optimization algorithms will fail to actually reach the global one. But with these algorithms, because they use random search, there is a lot of potential for them to reach the global minimum. The mechanisms are used for swarm robotics as well. So robots, several number of robots towards a particular sort of goal are utilized as well. So the idea basically is that we use these in various applications, complex science and engineering type of applications, and they of course use either towards single objective or maybe multiple objectives there may be that they would need to look into solving the problem. So collaborative robotics is an example of applications in the area of engineering, and also swarm robotics, as I mentioned, or other applications where these are being used. There has been, of course, a lot of work in the area of this bio-inspired optimization, and specifically which they fall within the meta-heuristic algorithms. So starting from 1950s and all the way, of course, up to now, here is, of course, a snapshot of the sort of works which have been carried out up until 2013, but of course, there has been a lot more beyond 2013 as well. And so now, one of the things which these particular algorithms do is the following. There are two basic, in fact, components in the algorithm which are being realized. And these components are the so-called diversification or the exploration sort of phase, where the algorithm actually carries out a quick search of the search space to identify a region within which there is a potential solution. And then after that, once that region has been identified, there is the intensification phase, or the exploitation phase, they call it as well, is initiated, where there is going to be an intensive, in fact, search then carried out in that sort of process, basically to reach the global sort of point. So algorithms are designed basically on the basis of strategically combining diversification and intensification with one another, so that you have a overall efficient sort of algorithm, basically. So I'll give you a few examples. This is the first example I want to go through is bacteria foraging algorithm. This was an algorithm which was proposed by Kevin Pacino in 2020, and it's based on the E. coli bacteria behavior, the way actually they look for food, in fact, in intestine, essentially. And so they will be looking for location of high level of nutrition, basically. So this, and I'll of course, one of the problems which of course we noticed with this particular algorithm when it was developed, which I'll just tell you about it, in fact, and then we did a bit more work on this and came up with some modified versions of this algorithm. The actual algorithm, the way it works is like this. There is a phase of so-called chemotaxis, which comprises tumble and swim. So the bacterium will carry out these two movements, basically. And the other thing which also along the line is the reproduction sort of phase, where some of the bacterium is removed and they are replaced with new bacteria. And so in that process, of course, then there is some eliminations and then dispersal. So eliminating, of course, the weaker sort of bacteria and then the new ones which have been produced. So you have a new population, and then these are dispersed, of course, in the search space. Now, one of the problems with this is the so-called chemotactic size, step size. This is the measure of the steps by which the bacterium actually moves from one location to another. Now, that step size in the standard bacterial foraging algorithm, which was proposed by Kevin Pacino, is fixed. And the problem is when the algorithm reaches, in fact, the potential sort of solution, then the bacteria will be actually toggling around the solution because of this fixed, in fact, step size. So it's likely that it will not hit exactly the optimum minimum sort of location. So in order to, in fact, mitigate for the issue, there has been attempts, in fact, to look at various possibilities, like using fuzzy logic approaches to affect the step size, or using adaptive delta modulation, or simple linear function, or in fact, linear function, quadratic function, exponential function. So a whole range of possibilities have been actually explored in the process. And I'll show you, in fact, what this means in the context of this application. Now here, this particular application is a single link manipulator. It's a robotic manipulator which moves on a single plane from a location to a desired sort of location. So there are some measurement sensors, accelerometer at the end point. There are two measurement sensors here at the hub. You have the hub encoder and also the tachometer. So that information actually is fed into the computer, and the computer will, of course, has got an algorithm which produces, of course, the control signal, which is fed through this motor and drives the system. The idea with this particular system is as far as we are concerned, because this particular link is flexible, we want it not to vibrate as the link moves. So, but of course here what I'm going to show you is basically the use of this bacteria foraging algorithm, the adaptive version which we developed in the context of modeling this particular flexible manipulator. So you have input, you have the output to it, and you develop a, let's say, an ARMA model, which is driven by the same input, which will give you an estimate of the output. Compare the two outputs with one another to give you an error, and that error is then used as a drive for this bacterial foraging algorithm to adjust the parameters of the model, basically. This is the structure of the model in mathematical sort of sense. And of course, the cost function which we are using in this case is the sum squared error. So the error is defined by this equation, basically. And if you run the algorithm, here is, of course, a whole different algorithm we've run in here. The standard Kevin-Bassino algorithm is this one, which is given by that. You can see it's a very slow sort of algorithm, although it does reach, of course, the a good solution eventually, and linear function, quadratic, and also the exponential function type of algorithms, which are all actually converging very fast, in fact. So in terms of the eventual result, as you get in here, you can see all these algorithms will reach the same optimum point, but the benefit, of course, with these modified versions of the algorithm you get is the speed of conversion. So you can actually stop the algorithm around here rather than going all the way up there. So that's, of course, one of the achievements in there as well. You can also see the difference between the actual and also the estimated sort of outputs as well. This is the half angle sort of output, so doing very well. Another algorithm which is also interesting, this is a nature-inspired type of algorithm, I would say, a spiral dynamic algorithm. In nature, you see a lot of these spiral type of phenomena in the form of hurricanes, for example, and all the rest. And so that's also an area of inspiration. And so you can actually formulate a sort of mathematical formulation of the sort of phenomenon in this particular case, where you could have the radius of the spiral and also the angle by which you start, in fact, the spiral, if you like. So you could have shapes of this sort of nature, or maybe that sort of nature, but in either case, of course, you will have a global sort of minimum sitting in the middle in here. So the algorithm basically has, in fact, it runs in this sort of manner. So you have individuals are actually randomly placed in the search space, and the movement of the individuals are, of course, in the spiral sort of form, as I mentioned. The algorithm has got two loops. In fact, there is the inner loop, which is displayed here on the right-hand side. You can't see, of course, the text is too small there. The inner loop is for movement and evaluation of the fitness of each individual, basically, in here. And then there is the outer loop as well, which relates to the extraction of best solution and updating of the center of the spiral. And so this is, of course, an example of the nature-inspired type of algorithm. And I'm going to show the result of this one in the context of this stair climbing wheelchair control which I think was also, I explained this one in a previous presentation in the conference as well last year, if you might recall. So here the idea basically is you've got a wheelchair in the four wheels, but you transform it into 2 wheels basically. And then all sorts of maneuvers, but in this particular example, we are looking at affecting this one to climb the stairs, okay, up and down. We use fuzzy logic in this case, so you have a whole range of activities in here. For example, for the landing, stabilizing, for example, rear wheels control, front wheels control, and also the tilt angle or the seat sort of angle, basically. Several sort of fuzzy logic controllers are there. Now, so we have in fact 12 fuzzy logic input-output scaling factors in here to optimize in here. And so, and of course, each of those fuzzy logic controllers will have this sort of form. So you have the input scaling and the output scaling. And the objective function is to minimize the tilt angle and the wheel's positions according to the nth step. So you have 2 wheels, of course, and you've got the tilt angle. So you can formulate again in fact, an objective function in the form of, let's say, root mean square sort of error. So you have these 3 error components. And in this particular case, the cost function, which is formulated, is basically the weighted sum of those 3 errors in this context. And so here you can see the results, of course, are, if you look at heuristic sort of tuning by the solid sort of line, or the spiral dynamic algorithm sort of tuning, the dashed line, they do seem to be matching quite well. However, the important thing, in fact, in here is the tilt angle, how the robot stays upright, in fact. And so you can see that the heuristic tuning, which is solid line, gives you a lot of variation, in fact, in the tilt angle. So deflections, but of course, with the spiral dynamic tuning, you get stable sort of situation in the upright as well. And here, of course, are examples of the actual and the estimated, in fact, output. Sorry, too far. The next example I want to actually touch upon is swarm particle swarm optimization. Particle swarm algorithm is basically using these 2 key relations. So you have a velocity sort of relation, velocity update relation. 2, in fact, terms in here relate to the individual particle sort of behavior here, and also the collective behavior of the whole swarm, basically. So you have the best position, and if you like, of the particle in relation to its current position, and then the global best position in relation to the current sort of position as well. There are a couple of random numbers as well, which are being utilized, and also these factors C1 and C2 are also utilized as acceleration coefficients, we call them. C1 relates to the cognition of the factor of the individual, and C2 is the social factor, which relates to the whole population or the whole swarm, basically. So that's the velocity relation. And here is the distance relation, or the position relation as well. So once this equation has been implemented, then you can update the position as well. There has been, of course, modifications, in fact, of this particular algorithm to a large extent. And one of the things which has been done is to incorporate this inertia coefficient in front of the velocity term in that equation. The idea basically is to ensure that these particles do not actually fly out of the search space. So this is basically a way of limiting their velocity so that they stay within the search space. And I'm going to now apply this to another example. This is a twin rotor system, which is replicating the behavior of a helicopter in a laboratory setting, of course. And the idea in our case in here is to ensure that it stays in the hovering mode without motion, in fact, in the vertical sort of axis. So you can consider this as a scenario of, let's say, a helicopter in a rescue operation, picking up maybe someone, and it has to stay, of course, still at a certain altitude. And I'm going to use in here basically the concept of what we call command shaping for vibration reduction. Now, if you have done, of course, vibration control, and if you have done looked at structures, the way they vibrate and how they do, basically there are certain frequencies at which you have a dominant level of vibration appearing in the structure. And those ranges or those frequencies we refer to as the resonance frequencies. And so you can actually formulate the behavior of a mechanical vibrating system with this simple second order, in fact, transfer function for each vibrating mode. So if you do have, let's say, 3 or 4 vibrating modes, you will have 3 or 4 of these transfer functions which you can put together in cascade and so on. Now, what we would like to do basically is to reduce these vibrations at those resonance modes. Okay, so one of the approaches is this, the command shaping technique, as we call, is to develop a set of impulses at certain locations and also, in fact, with certain amplitudes. For example, a 2-impulse type of input shaper would be located. One of the impulses would be at t equal to 0. Another one will be at pi over omega sub d, where omega sub d, of course, relates to this natural frequency of the system and also the damping ratio, in fact, related to that particular mode of vibration. And then, of course, the amplitudes are A1 and A2, as you would notice as well. So the parameter K also is dependent on the parameters of this particular vibrating mode. So in order for you to design, in fact, the command shaper, you need to actually execute such equations. And for those such equations, you need to have these parameters, the undamped natural frequency and the damping ratio related to each vibrating mode. And that could be quite tedious, in fact, and the measurements and, in fact, or the calculations may not be as accurate either. So what we did was to actually formulate an automatic approach for designing such command shaping mechanisms. So this is, again, in fact, making use of this bio-inspired optimization. Particle swarm optimization is utilized in here. So what we have is we've got a command shaper, which we're going to design in here. So these deltas, delta 1, 2, 3, actually designates the location of the impulse, and K1, K2 are the amplitudes, in fact, of the impulses which you have here. So these are all put together to give you the overall command shaper applied to the system. And then, of course, here you will have a desired response you want to have. This is the response of the system. Compare the two to give you an error, and that error is utilized by the PSO to then adjust these parameters, deltas and the Ks. And of course, one of the design rules in here, which we need to make sure happens is the sum of these Ki's is equal to 1. So here are some results. So we apply, in fact, the so-called bang-bang input to the such system in principle. And so a bang-bang input, of course, if you apply it, amounts to a lot of vibration. And so the shaped input, which we have now, will be of the sort of shape. You can see this dashed sort of, the solid sort of line. A zooming of that is actually indicated here. And if you look at the results, basically this fluctuating sort of signal is with the case of bang-bang input applied to the system, but the solid line is in the case of this shaped input applied to the system. And you can see, of course, quite significant reduction in the vibration appears in there. If you look at it from the viewpoint of resonance modes, for this particular system, we have one dominant resonant mode, which is at a very low frequency, basically around here. You can see, and so you can see what this input shaping does. So for the bang-bang input as it is, you can see that the I've lost my cursor. Sorry. So you can see this. The bang-bang input actually has the energy distribution of that is actually here like this. You can see. Okay. So by applying the command shaper, you get this sort of input basically. And the important thing is at this location, which corresponds to the resonance or the structure, you have this large dip. And that's, in fact, the secret behind the reduction of vibration. And you can see here also the outcome in the way of, if you have, without the bang-bang input, you've got, gives you a lot of peak in here, but with the shaped input, you don't have that peak. And that's, of course, an indication.
Professor,
yes.
We are running out of time, so
yeah,
can
we are finished.
Yes, yes, please.
Yeah, you're finished. So just to conclude to you, what I've done is to give you an indication of the swarm bio or nature-inspired swarm intelligence. So there are opportunities for you to solve complex optimization problems. You could use maybe single or multi-objective paradigms. These, of course, approaches will tackle unimodal and multimodal type of dynamic phenomena for you. The convergence to global minimum solution is pretty much very likely. In contrast to the, in fact, conventional techniques, which are actually failing a lot of the times. So I've given you a sample example of a few algorithms in there, of course. And of course, the applications are not specific to the ones which I have given you. There are lots of other applications you can use this in science, social sciences, and economics, so on and so forth as well. So thank you very much. So that's the end of the presentation. Any questions at all?
Are there any questions? Yes, please. Oh, okay. The mic is there. So, yes.
Doctor, when you use the spiral dynamic algorithm in wheelchair, what is the benefits of minimizing the tilt angle and the wheel positioning? I think it will minimize the degree of freedom.
So in the case of the wheelchair, what we have is, the important thing is here. Now, if I can show you, now look at it like this, okay? So this is, in fact, the wheelchair, so sitting in the upright position. This will be on two wheels, okay? When it is on two wheels, it's an inherently unstable system, okay? And so here what we want to do is, we don't want this actually to fluctuate in this direction, you know?
Okay.
So we want it to be balanced. So what when I say tilt angle, we mean this angle relative to the vertical line, okay? We want to minimize that so that it is staying upright, in fact, straight, without any fluctuation. Okay, so that's the benefit of the reducing that, and of course the wheels, of course, we positions we control also in terms of the direction control. So to make sure that the robot, in fact, or the wheelchair, travels in the right sort of path.
Okay, thank you, Doctor.
Thank you.
Thank you very much. The first question is, when we get the result, is there any form or criteria to assure or to get validation of our optimal solution for the problem? The second, what the kind of controller do you use to execute the programming or simulating model? Thank you very much.
Thank you. Yeah, in terms of, yes, there is validation, of course. There is a process of ensuring that you do reach the minimum location, for example. So if so here we have a cost sort of function in the form of, as an example, the sum of error square, for example, so that cost function has to be reduced to a certain level. And so here is, in fact, a snapshot of the evolution of the cost function. So, and of course, once it reaches, of course, a certain sort of level that we desire, then that's, of course, what we would like to have. So in each iteration, as the algorithm is run, this cost function value is being evaluated. So that's one way of evaluation here. So then in terms of the controllers, it depends really on the type of controller structure that you are going to use. And of course, depending on the application which you want to have. For example, if I were to use basically a flexible manipulator system, I will be okay to develop maybe a PID controller. So a PID controller I could design for it. But in case of the wheelchair, which I showed you, which is very complex, in that case, someone would probably want to use fuzzy logic sort of controller. And that fuzzy logic control could be PD-like or maybe PID-like, depending on what you want to achieve at the end of the day from it. So it depends really on the application, the type of controller you want to design, basically.
She's asking about the hardware of the controller. What
okay.
Hardware? Is it? Did you use, for example, Raspberry Pi or Arduino?
Okay, yeah. Okay.
This.
Right. Okay. Again, that's of course a case one would need to look at in the context of the extent, in fact, or the complexity of the controller you're designing. And that again relates to the application. If I'm going to use, for example, this flexible manipulator system, the dynamics of the system are basically dominant within a range of up to 80 hertz, okay, something like that, which is very, very low sort of frequency sort of range. And so in that case, I can use maybe a Raspberry Pi, maybe Arduino, for example, a simple sort of control, hardware. But if I'm going to use maybe a system, let's say in the context of, let's say, noise control over a head, let's put it in this way. Let's say if I have a system where the dynamics are, let's say, over a range of, let's say, 0 to, let's say, 1,000 hertz, okay? In that case, of course, the sample times are going to be very small, and so I need more powerful hardware, okay? Then I would need to go to a more specialized type of signal processing sort of device. So the way you want to actually decide on these choices is to look at your system, the range of dynamics of the system that you want to control, and simple Nyquist sampling theorem will tell you the target, the sampling frequency that you will need, and that will then tell you what sort of capability you would need to have for your hardware. So in our case, we have, for example, for this flexible manipulative system, I've used a desktop computer, for example. So that's, we can do with that. It was quite, a simple sort of mechanism to utilize.
Okay, thank you very
Okay.
much.
Thank you.
Thank you very much for
You're
your
welcome.
presentation. We will see you in person, maybe in the next conference.
Inshallah, yes.
Okay. Thank you very much.
Okay. All the best. Thank you.